So we were working on SEQUOIA, and we were actually studying hydrogen dynamics of zirconium hydride. And so metal hydrides are of particular interest lately because they're candidates for storing hydrogen. So on the left here, we have a cartoon of zirconium hydride. The zirconium, obviously the big red guys, the interstitial hydrogen, the little green ones. In order to understand these systems for this purpose, what we're really interested in knowing more about is the dynamics of the hydrogen in the material. And to that effect, we're going to be using inelastic neutron scattering. Obviously, we've heard a lot about how you can't really see hydrogens very well with X-rays, so that's sort of an obvious choice. And then in this experiment, we're actually going to be comparing our data to this idea that we can actually approximate the hydrogen as being bound as a harmonic oscillator for a particular range of energy. So in accordance with that model, we're actually going to expect that for relatively low energies, and by that I mean below 800 MeV, that will have basically equally spaced energy levels. So sort of a spoiler, we are going to choose SEQUOIA. So the reason that we're doing that, so to start off with, we know that a direct geometry would be nice because we'd like a nice dynamic range, and also to have high resolution. We also know that for this experiment, we're going to be going with the thermal neutrons because we're interested in energies that are on the order of hundreds of MeV. And then having decided that, we also know that we want to look at relatively high resolution because we want to be able to really look at the features of the excitations that we're seeing. So
we'll mention that we were looking at direct geometry beamlines, which all work on the same underlying principle of you have polychromatic neutron beam that comes, interacts with your Fermi chopper to generate a monochromatic neutron beam depicted by this solid red arrow. These neutrons will then interact with your sample, scatter off of your sample, and hit the detectors. Because we're looking at inelastic scattering, we care about the energy changes that you see when you scatter. So if you hit the sample with a certain energy, excite a phonon, the neutron will then lose energy as depicted by these rainbow arrows. And our goal is to figure out what each color in these rainbow arrows means. Our samples were loaded in aluminum cans because that aluminum has a fairly low neutron cross-section, which makes it a pretty nice background. However, if you're really worried about that background, you can use a vanadium can, which means you'll see diffraction, but you won't have any diffraction rings. I think I said that backwards. We are also interested in looking at these at very low temperatures, which means we need to use this closed cycle refrigerator, which will eventually be under vacuum, which means that we have to ramp temperature and put our system under vacuum, which makes sample insertion times kind of long and annoying. So the nice thing about this refrigerator in particular is that it has 3 sample holders that it can rotate. So instead of, pumping your sample down, waiting an hour, taking it down to temperature, waiting an hour, and then being able to collect your data and having to do that for each sample, you can just kind of rotate through, which is really nice if, say, you have to measure a background. One other really cool thing about SEQUOIA are the detector banks. For scale, you see these happy Beamline scientists. And you will notice that you can see 2 detector banks on top of each other. There's also a 3rd detector bank at the very top. And then even above that, there's space for another detector bank. So including what you can see at the very bottom, there is space for 5 levels of detectors. Currently, they are using 3. You will notice that there are gaps, but these gaps are offset between the layers so that if you, say, fold your detector in half, none of the gaps will overlap. So you have a really solid coverage through wide ranges of Q space, your diffracted angles. The really big range is nice because that means you don't lose neutrons even if they're coming off at large angles. So you are getting just more neutrons at your detector. The other thing that will help you collect as many accurate energy readings as possible is that this entire system is under vacuum. So you have this 2.5-story vacuum chamber so that you have no interactions with air once you scatter neutrons off of your sample. So these detectors allow both for Q resolution because you can see exactly where on each tube your neutron hits because you will the neutron will come in, it will interact with these helium little circles that I've drawn, generate a current, and go through that wire. That's that long gray line. And depending on where they interact with the wire will have a different voltage reading because of the resistance that you have to go through between where the neutron is interacting and the end of your detector. So to kind of summarize the slide, this detector bank is really cool.
This will be a very good example to show what spectra you expect to see from SEQUOIA. And we measured the zirconium dihydride under the incident energy of 60 MeV. And this is a 3D plot. The x-axis is the Q range. It's come from 0 to 5. You can see this plot shows a weird shape. This is because some of the Q and the E combination is not available by this instrument setup. And the y-axis is energy transfer. And you can see it can be positive or negative. This means the neutron can gain energy or lose energy. You can see, and another dimension is represented by the color. The red is the most intense, and goes to darker and darker, it goes to less and less intense. You can see most of the neutron, they just penetrate the sample directly. So they show the very intense peak in the elastic and quasi-elastic region. For the inelastic region, the energy transfer goes decrease. And if we cut from the Q equal to 4, we can see this slide. The energy transfer goes decrease, but there is a peak here. It's this region. There is a phonon peak. We can see clearly from here. And this one shows you the simple can, which Eve just shows you a few seconds ago. This is an aluminum can. You know, aluminum has a very small cross section. So the most neutron just go to the elastic scattering and they go to this band. You can see the inelastic region, they have very less signal. You can't really tell anything from here. And this is the sample we measure before subtract the background. And this is after subtraction. You can see there's very different between these two. So when you subtract the background, you're supposed to get a very clear signal of the sample you're going to measure. And Junchuan is going to show you some more pretty picture about the harmonic.
And this is what we measure this material at a higher energy of 1000 MeV. And the left figure, we can see this is the 2D plot of the energy transfer and the momentum transfer. And we can see some horizontal high intensity stripe, which correspond to some of the phonon excitation levels. By integrating over Q, we can get the right curve, which we can easily point out the excitation energy. Also, we can also integrate over different excitation energy range and get the curves of the intensity versus Q. Jennifer will talk more about these data.
Thanks. So now we're going to turn this around to you, actually. We're going to do something called an active learning exercise. It's called Think, Pair, Share. And so what we're asking you to look at is our data here. This is the intensity, and this is the energy. So we're asking you to think about, does our data support that hydrogen in zirconium hydride behaving like a harmonic oscillator? So I'm going to ask you to think about it for about 10 seconds, and then turn to your neighbor and talk to them for about 20 seconds about whether you think it is or is not a harmonic oscillator and why. So take about 10 seconds to think. person you were talking to thought. Anyone raise your hand? Yes.
No. We got a very strong maybe over here.
Can you say why you said no?
I guess because of the width of the peaks are kind of going to be
The width of the peaks. Do you mean the full width at half max, or do you mean the spacing between the peaks?
no, the width of the whole peak.
Okay, the width of the whole peak. Great. So that's definitely something we can look at, the width of the peak, and whether that is consistent. And I think we can agree that it is inconsistent through the energy range. What did anyone else think? Does someone have a disagreeing opinion? Does someone think it was a harmonic oscillator? Okay. Well, I think we could take a look at what does this mean? What does the spacing between the peaks mean? So the spacing between the peaks here is essentially the spacing between energy levels in a harmonic oscillator, which I suppose you may or may not be familiar with, and we did not specifically introduce. But in general, if the spacing between these peaks is consistent, it means that the spacing between the energy levels is the same. And that is what you would look for in a harmonic oscillator. But you're exactly right, that the full width half max here, it is increasing over time. So essentially what the researchers, and we agreed with them, concluded was that because this is linear, at least through to this peak, this is harmonic oscillator behavior, but at higher energy range, you are able to see anharmonicity growing in. And interestingly, I was talking to one of the speakers from this morning about data that had been collected maybe earlier this year on the like low resolution chopper diffraction. Yeah. Oh, great. Thank you. And so previous data showed that this was a harmonic oscillator, but because SEQUOIA is a high resolution inelastic neutron scattering instrument, they were able to resolve the anharmonicity. So one more think, pair, share, and then we'll finish up quickly. We see this background here increasing over the energy range. So why do you think that might be? Please talk to someone next to you and come up with a hypothesis. Great. Okay, so does anyone want to offer what they think the reason for the increasing background over energy ranges? Yes.
More thermal vibrations?
Thermal vibrations. Okay, perhaps, though we're saying same picture. Anyone else? There were people talking.
We can see you.
Yeah. Yes.
We know why, but we think it's a detector, like it's either geometric or like physics detector limitation.
Sure, that's a totally reasonable hypothesis. No, I mean it is. That's a totally reasonable hypothesis. So what we're going to say is that this data, we can't tell from this data whether that is or isn't true, but that's totally reasonable. But what we, basically the conclusion is that this background is from multiple scattering events. So as you're increasing in energy, you're sort of exciting more multiple scattering events, and that's why you're seeing an increase in intensity over space. So in conclusion, these are the 4 inelastic neutron spectrometers, and this is the phase space that you can work in when you're deciding which one you'd like to use for your experiment. So if you need thermal neutrons, cold neutrons, coarse or fine resolution, there's a full suite of instruments available here that complement each other. The Beamline scientists that we worked with, Matt Stone, wrote a paper that is available online about sort of comparing and contrasting these instruments. Oh yeah, he also made that figure. So we want to thank DOE, Oak Ridge, Argonne, NXS, and this is Matt Stone, this is Victor that we worked with. Thanks so much for listening to our presentation.
You said that there's both positive and negative energy gain and energy loss, but you only showed the results for positive, so what happened to the negative?
Oh, for, sorry, you can.
Yeah, so the intensity of the negative energy tends to be a little bit less, if at all, because it is possible that the neutron will kind of steal energy from the lattice, but it is, for physics reasons that I don't know, physics is hard. It is more likely that the neutron will excite a vibration, especially if we're at very low temperatures, which we are at 7 Kelvin for these measurements.
Yeah, at 7 Kelvin, you don't have a lot of excitations to give to the neutron. It's easier for the neutron, can still give them to the lattice.
The Bose factor.
Because most the electrons, they stay in the ground state, so they can only get excited up, and this like less populated on the excited state to give energy to neutrons.
Yeah.
Anybody tell me why the Beamline is called SEQUOIA?
No.
Oh no. Oh. Oh, Francisco knows. Francisco knows.
It's like so whenever this person who came up with a sort of alphabet for the Cherokee people, and he's like the only person in recorded history who has come up with an alphabet, like the single person for
Yeah.
community.
That people actually use, as opposed to like kids in middle school. Yeah. Cool.
Super cool.
Yeah.
So you mentioned earlier about the hydrogen storage capability of this zirconium hydride, right? So how does your hypothesis of this harmonic oscillator or related to the hydrogen storage thing that you mentioned? Is it related to this?
Well, so one thing that we didn't do that was done in previous experiments is they actually increased the energy enough to kick the hydrogens out. And I think that if you're interested in looking at sort of what it takes to get the material to actually release the hydrogen, that's probably an important step.
And that was about 1.5 eV.
Yeah.
That was what it was. Yeah.
In this compound, is there just one hydrogen position in the unit cell?
No, it's an interstitial positions. So many.
It's interstitial, lots of different near neighbor environments?
Yes.
To our knowledge, there is very little hydrogen ordering in the material we have looked at.
Well, what I'm curious whether, so there's an ensemble of hydrogen positions. Do you have any kind of fidelity to see different hydrogen positions if they're bound differently in the material?
So we were looking at a powder, which means that we could not use this for a sample. But if you had a single crystal of this material, you could, because of the detector bank, which is pretty cool, they are able to resolve the diffracted Q space as well. So I think you could get some sort of information from there.
That you could. Okay.
Thanks.
All right, thank you.